Hi, exam 2 review. So, chapter 3, 3.1 through 3.11. And we have 10 questions, 100 points. I believe this one is 13% of your grade, and keeps disconnecting, reconnecting now. Bandwidth issues? I don't know. Anyway, so that's our chapter 3, and the topics. We start with number 1, limit definition of the derivative. You guys had this question already on your first exam. This is the good old limit h goes to 0 of f of x plus h minus f of x divided by h. This time we say find the derivative. On your previous exam we said find the limit, so it's the same thing. Number 2, basic derivative rules, and we are talking about all of the basic derivatives that we have: constant, polynomial, exponential, log, trig, right? So basic derivatives with formulas, inverse trig. So those basic formulas, and then we go with the product plus quotient rules, which are the two formulas you have there. Number 4, I'm going to put the chain rule. We said that one is insanely important. Definitely at least 2 or 3 chain rules on a test. Then we have, from the special, we have implicit differentiation. Number 6, we have logarithmic differentiation. We have 2 types of word problems. The rate of change. This is where we did velocity, acceleration, and that cost function analysis and all that kind of stuff. And then related rates. Related rates was 3.11. I believe this was 3.5 or something like that. 3.6. Actually, I can just look here. 3.6. 3.6. And finally, tangent line. Why is it red? One problem that is never going to leave you is tangent line problem, because that gives you linear approximation. Linear approximation is power series for Calc 2. You have the stuff going into Calc 3, in curves of linear approximation, linear algebra as well, differential equations everywhere. So tangent line is just going to be upgraded and repeated and all of that stuff. So all of your exams in Calc 1 will have tangent line. Exam 2, exam 3, final exam, all of them. So make sure you know the procedure for a tangent line. And we had a special separate lecture on tangent line for those who showed up, right? And on that day, what we did is we outlined we said what a tangent line was. This is not a section in the book. This is the concept of the tangent line is in every single section of chapter 3. but I wanted to make it as a separate lecture so you understand that the tangent line is the central problem of Calculus 1, and we talked about it a little bit. I gave the procedure. So what you see here in purple is the procedure for the tangent line, and as you can see, the line number 1 is why tangent line problem shows up in every section of chapter 3. In 3.1, you get the derivative by using the limit. In 3.2, you get the derivative by looking at the graph. In 3.3, you get the basic rules. 3.4, you get the trick. 3.5, right? So product rule, quotient rule, and so on. So every section was taking different type of the derivative. Entire chapter 3 is teaching you to take derivatives. Number 1 over there says, just get a derivative. What derivative? Well, whatever section the function falls into, right? So this is why tangent line is the problem that overarches the entire chapter 3, right? You're going to use whatever needs to be used to calculate that tangent line. So implicit differentiation, logarithmic differentiation, quotient, product, chain, basic, inverse, trig, all of them fall into get the derivative, right? And then to find the slope, you plug in the value given to you in that derivative, and then find the y and do mx plus b to find b, you're done. Number 5, right? Win. So that's the deal for the tangent line. And as I said, you are guaranteed to have the tangent line problem on exam 2, exam 3, and the final. No questions asked. You must have it. Otherwise, all exams are garbage. Right? That's it. You see that I mushed all of the formulas in here. I know that inverse trig was 3.10. But again, you are memorizing specific formula. It is not a rule. It is not, right? It's just a formula. So all of the formulas, that derivative of cosine is negative sine, derivative of ln x is 1 over x, right? All of that is basic derivatives. More complicated stuff, obviously, is product rule, quotient rule, chain rule, right? And all of these good things later on. So you have basic versus more involved things 3 through 6. 2 types of word problems. So you are expecting at least 2 out of 10 problems to be word problems. 1 per. If you want more word problems, we can definitely put number of related rates and stuff, because related rates are great. They make you money in engineering. We saw problems in class, so you understood, hopefully, how important those are. And that's one of my favorite sections, actually, of Calc 1, related rates. I think that's all I had to say. No graphing calculators, that's the rule, right, of the department and RVCC. Bring in either scientific calculator, or you can just do the solar calculator, right, the one that just calculates the numbers. And that's that. Now, do you have any questions for me to solve? Yes.
Well, it's more of a general thing. If you could just, in general, go over chain rule with an example.
Yes. Chain rule with the example.
Like, I get it, but I feel like I just need to hear it.
So chain rule is going to have layers, because it's the derivative of the function composition. And we said you take the derivative of the outer function with the inner still plugged in, and then you multiply by the derivative of the inner function. That was a chain rule. So the simplest probably example would be to have, let's say, x squared plus 6 cubed. That would be the simplest. Because in this case, you see that the outer function is x cubed. If you are to just call this x, and then you have x cubed. So that would be 3x squared. 3x squared. But now instead of x, you're not writing this x, you're writing whatever was in here. And then the derivative of that is what's called chain, in our case 2x. So that's what the chain is. The chain is this extra piece from the derivative of the inside. And now I have this as 6x, x squared plus 6, everything squared.
So the 3, so then technically x cubed is f of x, and then
Yes.
x squared plus 6 is g of x,
Perfect.
and then you multiply it.
Because you are multiplying the outer
Yeah.
and the inner functions.
Yeah, and then you just did 3 times 2.
Or if you're stupid like me and decide to distribute the square into that, so it'd be 6x plus, well, x squared plus 6 times x squared plus 6, and, put all that.
Here,
Yeah.
yeah, it's just extra work for no reason, because we like it in a factored form. The reason why we like the factored form is because of chapter 4, as you see, you set it equal to 0 to find either critical points or inflection points, right? So we want it in a factored form because it's nicely set up for us to set each factor to 0 and solve it quickly. If you FOIL it, then you are making your life, right, more difficult to solve chapter 4. Chapter 3 is there to set up the mood for chapter 4, right? And then we go there.
So flying loop.
So that's the answer.
Yes, I hope you're not disappointed.
No, I just sure.
So when you have the factored form is when you notice expanding or simplifying.
Yeah, factor form is a preferred. Factor form also is supposed to have the least amount of calculations, which is important for computer science, right? The less calculations you have, the less calculations processor has to do, right? Yes.
I have a question. So I took a picture of it from the quiz from the other day.
Mm-hmm.
So, are you ready?
I was born ready.
All right. Find the second.
The second derivative, okay, so dy dx squared, also known as f double prime, okay, or also known as y double prime, or known as y with 2 dots. All of that is second derivative. All right, so find the second derivative.
Of 11x squared plus
11x squared plus
y squared
y squared equals
3.
3. Okay. We are looking for the second derivative of this. Now notice that I did not put the y up there because I am taking the derivative. So up to squares is the operator, and then you are taking the derivative of something. So in this case, you are taking the derivative of the mess inside. Okay, cool. So we are going to apply one of the derivatives, and the other derivative is still going to be outside. When I apply the derivative here, I get 22x plus 2y dy dx equals 0. So what did I do here? Well, dy dx is the dy dx is the chain rule because I took the derivative of y in respect to x, and when they don't match, you have to follow with the chain. So the derivative of y squared is 2y, and then take the derivative of y in respect to x is the chain rule that follows. Now, it's good to take another derivative here, but we are going to keep this line in mind, and we'll see why. So take another derivative. It becomes 22 plus, and now I have product rule because I have two functions over here. There is a 2y function and a first derivative function, right? So I have to do the product rule in between those. So copy the first, and when I take the derivative of the first derivative, it becomes second derivative, which is what you were looking for, plus copy the first derivative times derivative of the first, which is 2, and since I took the derivative, there is going to be another dy dx. It's going to be confusing as hell, but that's okay.
So every time you take a derivative when you're finding second or third derivative, you have to write y.
Every time you take the derivative of y in respect to x, you have to follow with the chain. That's the rule. Doesn't matter which derivative. Could be 70th derivative. It doesn't matter. First, second, third. You are always taking a first derivative. Fourth derivative is the first derivative of the third derivative, right?
Yeah.
In which case you can just rename them. If you had that the third derivative is equal to something, you can, instead of writing it as a third derivative, you can just call it g of x. And then the fourth derivative is just g prime, right?
Well, would we get it wrong on the test instead of writing d squared y over dx squared?
No, well, this is the notation. You can also write y double prime and so on. But the notation here is going to be a little bit tricky for those of you who do not have attention to detail, because this square here is only on D, and the square that we're going to have here is going to be on the whole thing. So that's going to be a little bit tricky. But we have 22 plus 2y d squared y dx squared plus 2 dy dx squared. These are not the same. This is the second derivative, this is the second derivative, and this is first derivative squared. It's completely different stuff. Okay, so now why did I say remember this line? Because this is the line where you can solve for the first derivative and plug here to eliminate it from the equation. We are technically done with this last line because we do have a second derivative. We solve for it and we're done. The issue is that we can solve for dy dx and plug in there. So here we are going to say that the dy dx is equal to negative 22x over 2y. When you move 22x to the other side, and divide by 2y, dy dx stays alone, right? So that's what we got from there, and we can reduce this to negative 11x over y. So that's the one that goes in there. So now I have, I can cancel 2's everywhere here as well. So cancel this, cancel, cancel, because when you divide everywhere by 2, 0 divided by 2 is still 0. Awesome. So I have 11 plus, that's supposed to be a y. Y times the second derivative plus, and now negative 11x over y squared equal to 0. Move these terms to the other side, so y d squared y over dx squared is equal to negative 11 minus 121x squared over y squared. And now get y to the other side, so divide both sides by y to get y alone, and we are finally done. So second derivative of y is equal to negative 11 over y minus 121 x squared over y cubed. You already had y squared. When you divide y squared, you take one more y, becomes y cubed. This can be simplified. MyMATLAB might look for simplified answer. We can factor this. So on the exam, I might be tempted to give the full credit here because, yeah. But this is really nicely set up for factoring, because you can factor negative 11 over y, and that gives you 1 on the first term, plus 11x squared over y squared on the second term. It's really nicely set for and then you can even push it into negative 11 over y, 1 plus 11 times x over y squared.
I have a question.
But yeah.
When you do y squared divided by y, shouldn't it be just y on the bottom?
No, it's y over 1, so you have a double fraction. You have 121x squared over y squared over y over 1.
Oh.
Right? So these guys multiply on top, these guys multiply on the bottom. So it's already divided by y squared, and you're dividing it one more time by y, so that's altogether y cubed. So I would call this the boss over here. Usually that's what I write on the test when someone pulls off the boss move. Yes?
My math lab, not to like algebra or whatever, but they like threw out the x altogether. Like, I don't know how they simplified it down to this, but they simplified it down to negative 33 over y cubed. So like, how do you even get rid of the x?
Well, probably from the original equation. Yeah. From the original equation, this is, again, it's just, at this point, it's just flexing, okay? Flexing in mathematics. No, it doesn't matter, but it's just flexing now. Because what you can have now, if you divide everywhere by y squared over here, right? You get this 11x squared over y squared plus 1 is equal to 3 over y squared. So you see this is the piece that I have factored, right? You see it here. So this becomes negative 11 over y times, and this whole parenthesis is 3 over y squared, becomes negative 33 over y cubed. It's just flexing. That's all it is. It's important for computer science because this clearly has less operations than any of the answers above. But that's their problem.
Yeah, but why does my math lab expect you to flex?
Yeah, that's what I don't like about my math lab is that sometimes the way that it wants you to answer it, it's not like what you would want us to do on the test.
They're just too extra.
They are just too extra. I love that. As I said, on the test, I'd accept the boxed answer. And then there's the boss answer. And then over here, we'll put the God tier. How about that? There you go. So you have the exam answer, the boss answer, and the God tier answer. How about that?
Math, I was trying to make this lots of gods.
Yeah. I mean, it's the discipline, so what are you going to do? All right, let's see what else.
Okay, do x minus 35 over square root of x minus square root of 35.
Oh. Like this?
Yeah.
Now what are we supposed to do with this?
Well, it's quotient first, but you gotta.
Are we supposed to differentiate?
Yeah.
Find the root?
Yeah.
Ooh, okay. We can do the quotient rule, or we could flex. Yes, simplify. We're going to flex. And there are two different ways in which you can flex here. Wow. So, the brute force to solve this is to use quotient rule. No question there, right? We all see division. We know it's a quotient rule. So if you want to brute force this problem, you do the quotient rule. However, we can flex a little bit and transform this into a joke of a problem eliminating quotient rule. So the way you would do that is two ways. One way would be to multiply by the conjugate of the denominator, which is root x plus root 35, and that would eliminate eventually the denominator. And for those of you that remember the trick all the way back in chapter 2 somewhere, I said, remember that you can factor anything. So you can factor this numerator into root x minus root 35 times root x plus root 35. As long as you have a subtraction of two numbers, you can factor it. You are used to a squared minus b squared to be a minus ba plus b. This is what you are used to in your algebra course. And you always wanted to have x squared minus 100, right? To get your x minus 10, x plus 10. But it's okay to have x minus 7. Because what have I done here? I took a square root of this number of x squared and it became x. And I took a square root of 100 and I got 10, right? So if I have x minus 7, then I can just have root of x minus root of 7. I can't compute them, so I'm just going to leave them, right? And that's how I did the same thing up there. I can't take a root of 35, just leave them. But then when you take a look at what you have at the denominator, right?
You just cancel out
It-
that.
yep.
And then you just reload it.
And you just have a basic derivative from that point on.
Could you do that if it was like x plus 35?
No. Plus
And then there was
plus factors over complex numbers. So no. Only negative, only subtraction.
I'm saying what if the denominator was a plus?
Oh, in that case you would have to rationalize, or you would have to
Like
do the quotient rule.
apply the conjugate.
Yes. Yes.
Now we're just left with
So now you're just left with the derivative of root x plus root 35, which is 1 over 2 root x plus 0. Root 35 is a number, so derivative of root 35 is just 0. And we don't worry about anything.
you don't want to rationalize, let's get rid of that.
No, because we don't have a value for x. X could be 4, in which case no reason to suffer. If x is 5, well, in that case, you suffer because it's 5. So there is no reason to preemptively suffer. Okay? Just leave it as 1 over 2 root x, and then if we have to find, let's say, we have to find tangent line, right? And the tangent line is at 3, then you have 1 over 2 root 3. You have to rationalize then. But if it's, tangent line at 16 and you plug in 16 there, then square root of 16 is 4 times 2, you get 1 over 8, nothing to rationalize. So, no extra work for no reason yet, until you see what x you get. So we'll just leave it that way. And if you do rationalize it, then you're not wrong. It's just you spent extra time, which you didn't have to. The rule is don't leave any square roots in the denominator that are definite numbers. So no square root of 3, no square root of 7, no square root of 13, right? You should not have those in your answers. But square root of x in denominator is okay, because we don't know what x is yet. Right? So we can leave it. And again, if you end up rationalizing it, well, that's fine. It's not going to be points off. Anything else that you might want to discuss? We have about 5 minutes left and then another 40 after that. Yes?
Could you do an example of tangent line?
Of course. Which one? Remember,
I
you're...
asked you about the one from the lab because I was working on Or can we change the numbers? Oh yeah. So-
Something, give me something
okay,
disgusting.
So the equation of tangent line.
Okay, so we are looking for the tangent line. So find the equation of the tangent line.
Y equals 3 plus 6x plus 9x e to the x. And then a can't be 0. Oh, a is 0.
Do I have the function correctly?
Yeah. Well, 3 plus 6x plus 9x e to the x, a is 0, yeah.
Bueno. Procedure for the tangent line says find the derivative. Okay. Derivative of 3 is 0, derivative of 6x is 6, plus, and now I have a product rule. Copy the first times derivative of the second, still e to the x, plus copy the second, e to the x, times derivative of the first is 9. And we can simplify this a little bit to get 6 plus 9x e to the x plus 9 e to the x. And to find the slope, we will plug the value into the derivative. So they want us to calculate this at a equals 0, which is x equals a, right? So it's 0. It's the value you plug in. And we have 6 plus, this is going to be 9 times 0 times e to the 0 plus 9e to the 0. All of this is just 6 plus 9 equals 15. The middle term is 0 because 9 times 0 is 0 times 1. E to the 0 is 1. So the slope is 15. Great. I have x value, which is 0. I just calculated that slope is 15. I need y. Now y is when you take 0 and plug in original function. So that's going to be 3 plus 6 times 0 plus 9 times 0 e to the 0, which is 3. And I just found that y is 3. Y equal mx plus b. Y is equal to 3. M is equal to 15. X is equal to 0 plus b. B is equal to 3. Tangent line is y equals 15x plus 3. This tangent line contained product rule in the derivative. So tangent line can be with basic derivatives, product rule, quotient rule, chain rule, implicit differentiation, logarithmic differentiation. So any type of differentiation, right, can be here. Now, let's say you care and you want to check this. You would go to Desmos and you would grab the tangent line. They must touch at the single point at x equals 0 in this case. So we have 3 plus 6x plus 9x e to the x. And that is going to give us, as you can see, this red line. I really have to zoom out a lot for you to see the curvature and stuff like that, but we'll just leave it there. And now, over here, I'm going to have my y equals 15x plus 3. And as you can see, it's very difficult to see, but the blue line and red line touch exactly at x equals 0, 3. Both have the y-intercept at the same spot, obviously, and the blue line is the tangent to the red line for this problem. Now, I have no clue how far I will have to zoom out for you to see the differences between, because at this point, it's very difficult to distinguish the red line from the y-axis even, right? Because the example is a little bit, as you would say, extra. Okay? Well, I'm trying to keep up with those terminology. So, yeah. Cool. Any other questions that you might be interested in?
Oh, God.
Yes?
Just looking for a good logarithm one. Messing me up.
This thing just exploded. Let's see if, yeah. So that was our problem on the tangent line, which had the product rule in a derivative. Remember the tangent line procedure.
You go up real quick.
What happened?
You go up.
Oh, you mean to scroll? Sure. Any questions? Oh my God. Boss, you got anything?
No, I'm good.
You're good?
Yeah.
No. You're good? No. We have like 4 people designated to ask questions. Oh, perfect.
How do you find this? I couldn't get this problem.
So that's the one of the, okay. So y equal cosecant inverse of x squared plus 1.
What? That's bigger than 0.
Yes.
Does that matter?
It does for the graphs and stuff like that. So not so much for the problem. So this is a cosecant inverse derivative. We covered this in 3.10. The derivative formula for cosecant inverse of some function is going to be f prime of x divided by the absolute value of f of x times the square root of f of x squared minus 1. No, 1 minus, I have this backwards. 1 minus f of x squared. So, all you need to do is to realize that your f of x is x squared plus 1 and that your f prime is 2x, and just plug them everywhere. That's all it is. If you know the formula, you are only dealing with the argument, and the argument is x squared plus 1. You can put anything here, it doesn't matter, right? So each one of the f of x's will be replaced by x squared plus 1, and this one is replaced with 2x, and you're done. So that's just reading the formula that it's given.
But it would just be.
So what about the
Cosecant is giving you the form for the formula, because each one of them has a different form as a derivative. So cosecant corresponds to that form. What's important is f of x that goes for each piece. So cosecant is not going to show up anywhere unless you have cosecant of cosecant, in which case.
And we have to know all those the 6 functions.
I hate when I second guess myself. I was right the first time.
Oh, you're killing me.
I know. It's squared minus 1. So, what's the derivative? What's y prime? It's going to be 2x divided by, and then we have the absolute of x squared plus 1, square root of x squared plus 1 squared minus 1. And you don't have to have absolute values around x squared plus 1 because that's always positive anyway. So we could simplify this one. Let's see what we can do using algebra. We have our x, so now we can just use regular parentheses, x squared plus 1, because it's always positive. And now when I FOIL, I get x to the 4th plus 2x squared plus 1 minus 1. And you see that this plus 1 minus 1 cancel at the end. And that simplifies the problem. So our y prime derivative is equal to, now I have my x squared plus 1. And I can factor x squared, which gives me x squared plus 2. X squared plus 2. And this x squared jumps out as x, so I have 2x divided by x squared plus 1 times x times the square root of x squared plus 2. And now these guys cancel, and we have the simplest form for the answer. So my MATLAB might ask you to go as far square root of x squared plus 2.
I have a question. Which, I'm trying to find in my number, which were the two formulas that...
The most important formulas for inverses? Inverse sine and inverse tangent.
Yeah.
Inverse tangent, definitely the most important one, because that one shows up in integration a lot. Inverse sine will appear in here and there, and it will appear also in differential equations a little bit. But inverse tangent is a definite, a lot of stuff down the line with inverse tangent.
That we have to know for the test, right?
As tangent x everything squared. That's what it means. And this is like taking the derivative of x squared. So it's going to be 2x to the first power, which is just 10x. And then the derivative of the tangent x is secant squared x. That's the chain rule. Now, we can't really simplify this because secant is 1 over cosine squared and tangent is sine over cosine. So the only other form you can write this in is 2 sine x over cosine cubed x. And I don't really know if you gained anything by it, right? Because tangent will have 1 cosine in denominator, secant will have 2 cosines in denominator. So that gives us altogether 3 cosines in denominator. And it doesn't really make a difference there.
So it's fine if we wrote it the first way?
Yes, the top is just perfect. So this over here acts as x squared, and the derivative of x squared is just 2x.
I have another. Can you do implicit kind of calculations cosine parentheses y minus 11 equals x?
The derivative of this one?
Oh, it's just only the y is in parentheses.
So cosine y minus 11. All right. So we have 3 terms. In this case, we do not have any product rule, quotient rule, nothing special crazy going on. We have the derivative of cosine is negative sine. And then I took derivative of y in respect to x, so I have to follow with the chain. Derivative of negative 11 is 0. And on the other side, derivative of x is 1. So now we're going to move negative sine y to the other side. So dy dx is equal to negative 1 over sine y. And we know that that's cosecant of y. So the derivative we're looking for is just negative cosecant y.
So whenever you find the derivative of just y alone, that's when you write dy over dx?
When you take the derivative of y in any form.
Because I was getting confused about that first one that we did.
Y is a function of x. So if y is a function of x, that means that y has some function to it, right? Y could be e squared. E to the 2x. Y could be cosine x. Y could be something, right? So when you take the derivative of it, it's going to have a chain rule.
But then how come with like the second derivative thing we did, if we wrote 2y and then d2y over dx squared? Why wasn't it just 2 and then d2?
Because it was a product rule. It was a product rule. Copy the first derivative of the second plus copy the second derivative of the first. Put parentheses around it and write product rule above. So that way you know. Because if I remember well, we have 2x times, right? Or something.
Well, it was fine due to...
No, I know, but just the part that we took the product rule for. He had the 2 functions, and I know one was it 2x dy dx? Second line in the middle of the problem.
My notes are...
Yeah, I can scroll.
The one where we found the second derivative?
Yeah, but before we found the second derivative, there was
2y.
2y. Yeah, okay, 2y dy dx. Yeah. 2y dy dx. So copy the first derivative of the second plus copy the second derivative of the first. Good.
Professor, we have to memorize the derivatives of all 6 trig functions, right?
Yeah, those are basics.
The second derivative of cosine x is just negative cosine x, correct?
The second derivative of cosine is negative cos. Yes. Yes. So for the trig functions, you have 3, and the other 3 are symmetrical. So that's the good part about it. So you are technically remembering 3 only, and then the other 3 are symmetrical. If you take a look at, let's say, the derivative of secant x is secant x tangent x. Well, the derivative of cosecant x was negative cosecant x cotangent x. So these two are symmetrical. As you can see, you have a secant, secant, tangent, cosecant, cosecant, cotangent. And all of the ones that are co, right? Cosine, cosecant, and cotangent, all of those will be negative in their derivative. And then sine, tangent, and secant are all positive. There's a lot of symmetry when you put all those 6 formulas one next to the other. And then once we start working backwards in 4.9 and going back and starting chapter 5 and then all Calc 2, these become basic integrals, right? When you see secant times tangent, then you will know that the integral of that is secant x. So all of these formulas will be flipped and you will be reading them backwards for integration, called antiderivatives. But that's 4.9. So the more you learn now, the less you'll have to worry later when other concepts, in addition to what we have, land on a pile.
Okay, here's another derivative for it.
Let's see what we have.
D over dx of cotangent x to the e to the x.
Like this?
Yep.
Ooh, nice. So this is a product rule, clearly, right? We have x times e to the x. That's a product rule. But that's buried inside the cotangent, which means we have a chain rule with a product inside. So I'm just going to label this as product rule within chain. Great. Now, what is the derivative of cotangent? Well, it's cosecant, negative cosecant squared. So it's negative cosecant squared of the same thing, x e to the x. And now we have to do the chain. And the chain is going to be the product rule. Copy the first, derivative of the second, plus copy the second, derivative of the first. So this is going to be, so it's going to be e to the x, and then x plus 1 is going to be a negative in front, and then cosecant squared of x e to the x. Now, some people might put x plus 1 in front, and then e to the x, and whatever.
Does it matter?
No. Because we just want it in factor form, because you will be setting each one of these separately to 0 for chapter 4, right? For critical point or inflection point or something, right? You set the equal to 0, so you have 3 factors. It doesn't matter which order you.
I'm confused where you get the x plus 1 from.
When I factor out e to the x, x plus 1 is left.
Oh,
Yes.
Do we have to go that far? Always? Like, always factor
Chapter 4, yeah.
in chapter 4 or currently we have to always.
Chapter 4 is coming up in 3 weeks. Not even. Right? It will be the best if you did the chapter 3 exam, chapter 4 exam the day before. If we have that Wednesday before Thanksgiving, that will be the most amazing date for your exam 3, because we would still have chapter 5, and when we come back, we only have 2 weeks, and then it's the final. That's it. 4 classes.
So is chapter 5 just on the final?
On the final. And then chapter 5 is everywhere on your Calc 2 and the rest of the life. So chapter 5 is setting up the integration for everything else. Yes?
Does it have to be in that order?
No.
So my math lab is like wanting a specific order. It would actually.
No, I think they would let you put in any. Generally, we like the trig last or ln to be last because they have arguments like this, so it's not confusing. But e to the x and x plus 1 in any order is fine.
Sometimes they don't. Sometimes they'll take it if you don't factor it down to it.
Up to my math lab. Yes.
So when are we supposed to finish chapter 4?
Will be done next week or following week. We'll be done because it's 9 sections. We already covered 4.
Yeah.
After the will be after the exam we'll cover section 5, and then we only have 4 sections left. So next week we might be done, or Monday following week we'll be done. Yes.
You said chapter 5 is going to be on the final?
Yes. Chapter 5 is the big deal for the.
Is it going to be like the main part of the final? Or is it gonna be
Nah, we're about 30% or so. Need to at least 2 definite integrals.
Okay.
I mean, generally, I give these sections for those students that are going to Calc 2. Those of you who do not learn 5.5, do yourself a favor, do not sign up for Calc 2 until you know 5.5, like your name, backwards and forwards. Because about 90% of your Calc 2 problems will end with 5.5 section, and if you don't know, use substitution and chain rule. It's just waste of time and money. So, but we'll deal with that the last day of class. You'll know by then. Any other questions for exam 2 that it's coming up on Monday? Oh, sorry, no Monday. On Wednesday in 2 days. All right. I'll see you all on Wednesday.